What the new gravitational wave catalog reveals about black holes. For years, black holes were cosmic dead ends. You could not see them directly, only infer them from what they did to everything around them. Now, instruments on Earth have picked up 128 new gravitational wave signals in just 9 months, enough to more than double the size of the major catalog of these events. That changes the question. The story is no longer whether we can detect black hole collisions at all. The story is what kind of universe produces this many violent mergers, and why so many of them look stranger than expected. This matters because gravitational wave astronomy has crossed a line. A decade ago, one detection was a revolution. Now, the detections are turning into a census. And once you have a census, you can stop treating black holes like isolated curiosities and start asking bigger questions: how they form, how they grow, whether Einstein still holds in the most violent conditions in nature, and even what these collisions can tell us about the expansion of the universe. To understand why this new catalog matters, start with what LIGO and its partners are actually doing. These observatories are not looking at black holes with cameras. They are measuring tiny changes in the travel time of laser light inside giant L-shaped interferometers. When a gravitational wave passes through Earth, space itself stretches and squeezes by an absurdly small amount. If the same pattern appears across detectors separated by continents, and if the signal matches the waveform predicted by general relativity, then the universe has effectively sent us a chirp. Not light, motion in space-time itself.
The first time that happened, in 2015, it felt like a once-in-a-generation event. The new catalog makes it feel more like a new branch of astronomy, finding its rhythm. The March 2026 release covers signals detected between May 2023 and January 2024 and includes black hole-black hole mergers, black hole neutron star systems, unusually unequal pairs, and rapidly spinning systems. That variety is the real headline. The universe is not repeating one clean template. It keeps handing us new versions of the same catastrophe. The standout example is the heaviest black hole merger ever seen in gravitational waves. The two objects that collided were each around 100 times the mass of the Sun, producing a final black hole of about 225 solar masses. Most detected merging black holes are closer to a few tens of solar masses. Push the masses that high, and the ordinary story, where massive stars live, die, and collapse into black holes, starts to strain. The leading interpretation is that at least some of these monsters may be second-generation objects, black holes built from earlier mergers, then thrown back into dense environments where they merged again. That possibility matters because it tells you something about where these systems may be born. Maybe not in quiet stellar pairs evolving alone, but in crowded places where gravity keeps reshuffling the deck. Dense star clusters, galactic nuclei, maybe other environments where black holes can meet, merge, and come back for another round. The new catalog is starting to map the ecology of extreme gravity. And mass is only one part of the story. Another event in the catalog involved black holes spinning at astonishing rates, roughly 40% of the speed of light. There is also an unusually lopsided pair, where one black hole was about twice as massive as the other. These details sound technical until you realize what they mean. Spin and mass ratio are fingerprints. They carry memory of how a system formed. A simple, isolated binary should leave one kind of fingerprint. Repeated mergers or chaotic gravitational encounters can leave another. The more fingerprints we collect, the harder it becomes for black holes to hide their past. This is the moment where the catalog stops being a trophy case and becomes a laboratory. With enough events, scientists can ask whether black holes in the earlier universe tended to spin faster, whether certain mass ranges are more common than models predicted, and whether extreme systems are rare exceptions or signs that our expectations were too narrow all along. These detections are turning into the statistical foundation for a new kind of astrophysics. The catalog also matters because every one of these collisions is a stress test for Einstein.
General relativity has survived more than a century of scrutiny, but black hole mergers are where the theory gets pushed hardest. One of the loudest signals in the new release was clear enough to let researchers probe the waveform in unusual detail, looking for cracks between the real signal and what Einstein's equations predict. So far, the theory is still holding. The better our detectors get, the more precisely relativity survives.
Then there is the cosmology angle, and this is where the story widens beyond black holes. Gravitational waves can act as what astronomers call standard sirens. From the waveform alone, you can estimate how far away the merger happened. That gives scientists a new way to measure the Hubble constant, the rate at which the universe is expanding. Different methods have been disagreeing for years. The new catalog does not solve that tension, but by combining the full set of detections so far, researchers produced an independent estimate of about 76 kilometers per second per megaparsec. The uncertainty is still too large. But it shows why this field is bigger than black holes. We are learning to use collisions in deep space as cosmic measuring tools. What scientists still do not know is almost as interesting as what they do. They do not yet know how many of the strangest black holes are products of earlier mergers and how many came from some other formation channel. They do not yet know whether the apparent spin trends with cosmic time are robust or just early hints. They do not yet know whether gravitational wave cosmology will eventually help settle the expansion rate dispute. And for the most extreme events, they are still improving the waveform models themselves because signals from huge, fast-spinning systems are hard to interpret cleanly. But that uncertainty is not a weakness in the story. It is the payoff. A decade after the first detection, gravitational wave astronomy has moved from proof of concept to population science. The universe is no longer giving us one dramatic chirp every once in a while. It is starting to sound crowded, messy, and more inventive than the neatest textbook picture of black hole formation. That is the real shift in this new catalog. It is not just that we heard more collisions, it is that the collisions are beginning to tell a larger story. Black holes may grow through repeated mergers. Extreme gravity is still obeying Einstein under terrifying conditions, and the same ripples that reveal dead stars crashing together may also help measure the fate of the universe itself. And if this is what we can learn from individual chirps, the next question is even bigger. What happens when we stop listening for single collisions and start trying to hear the background hum of all of them at once?